Hello, everyone. Welcome. Welcome back to our series with Steve Campbell. Steve, welcome back. We're doing another series on data modeling, kind of 101 data modeling basics. And Steve's walking us through all the nuts and bolts of what beginner users need to kind of go through for data modeling inside Power BI. Welcome, Steve.
Yeah, thank you very much. Good to be back. Hopefully, you have seen the last session. If not, no worries. It was recorded. The link will be posted at the end. You won't need it for this session, so feel free to go back and watch it afterwards, but we'll have a little recap anyway at the beginning.
And,
So
and I'll make sure I
if
snag the
you,
link for that for you and put that in the chat windows both on LinkedIn and YouTube, just in case you want to catch that one and get caught up on this after the session's over. All right, Steve, let's
yeah,
transition over to your screen. Let's get you going. All right, your screen's up.
awesome. Well, welcome. For those who were here last week, welcome back and thanks for joining me for part two. If you weren't, welcome to the series, and we're going to go through some data modeling. So I'll go through the introduction. I'll just introduce myself, and then we'll have a little recap on last week. After that, then we'll get back into this week's session. It does get a bit more advanced this week, which is great. So we're going to go through some more of the advanced topics, but hopefully at a beginner level so that we can see really looking at optimizing our data models and what that means. So again, this is me. So I run the Power BI team at Cognizant Microsoft Business Group over in the UK. I used to live in the USA. I lived in the same town as Mike, actually, and that's how we know each other. And I'm a data platform MVP. Please follow me on LinkedIn, is probably where I put most of my stuff, and that's where you can find any new training if I do that. So enough of that out the way. Let's go through a little recap of what we went through last week. Very high level. Again, feel free to go back and rewatch that. It's probably one, if that stuff was new, you might want to rewatch a couple of times. So again, recap from last week, we went through what were fact tables and what were dimension tables. Right? So our dimension tables contain descriptive information, whereas the fact contains keys to these dimensions, as well as values and also things to sum and add. We talked a bit about star schema, and this is kind of that optimal view. And this is really what we want to get when we make our models. We try and make the star schema, which is one or multiple fact tables surrounded by some dimensions. And you can see here the dimensions support filtering and grouping, whereas the fact tables support summarization. So another way I like to put that is, in a filters versus values. So we have the filters, which are anything that changes the numbers or alters how we view a certain measure. And these should come from the dimension tables. And then we have the values, and these are the numbers themselves. And we looked at, these are bar graphs, same as tables. It's just a number filters in a certain way. So really, this is how we break down Power BI. We have some values at its core, some numbers, which are measures from the fact table, ideally. And then we have some filters, which are dimensions and just different ways to slice and dice these measures. We talked through keys. I won't go through this in too much detail because we did go through it in a lot of detail last week. So please go and rewatch that session. We talked about a primary key, and that's something that uniquely identifies a row. So it's a unique value and it's not blank. We have a natural key, which exists in the data, and it's a unique non-blank value. Often these can be things such as employee ID, right? These were created in the data, created in this example of an employee ID. This is created by our HR team in order to track employees. We have surrogate keys, and these are created specifically for our database. So it's created for the star schema design and in the ETL process. And both natural keys and surrogate keys, could take that primary key constraint. And then we talked about foreign keys. So the primary keys, those natural keys, surrogate keys, they belong back on those dimension tables to uniquely identify each value. And then in order on the fact table to know which value we're talking about, we have a foreign key. So that just relates to the primary key of another table, which is a really good way. So ideally, in our fact table, we're going to have a load of foreign keys and then some values to summarize. We went through some role-playing dimensions. Again, I'll skip over this quite quick, but these were when a fact table has multiple columns that can be used by the same dimension, the same foreign key. Example is when we have an order date and a delivery date. It's called a role playing because in the date table, it plays two roles, right? It can play the role of being the order date table, and it can play the role of being the delivery date table. Went through slowly changing dimensions, which is when we have dimension fields that change infrequently. Customer address is a really good one. You know, every customer has an address typically, but sometimes they move, but normally they don't move that frequently. So that's why it's called slowly changing, because this will update, but not very frequently. We looked at three different types, kind of the retain, the update, and the insert. And again, these were just different ways to track these depending on our goals. And just the other things we covered at the end, degenerate dimensions. We'll cover this one a bit today, actually, and it's a dimension column that's stored in a fact table. So we see this often, right, with order IDs, transaction IDs, ticket numbers. These are typically values which we see in the fact table because they're very high cardinality often, but they don't have their own dimension because they don't have any other type of attributes. Junk dimensions, this was just one way of us combining small dimensions tables, few attributes. I don't see this too often in Power BI, to be honest, but we think it's important to understand so that if someone comes and tells you that this is a junk dimension table, at least you know what they're talking about. So really it's just for simplicity, right? Where we combine all these little tables and just put them in one big table. And then we also said a factless fact at the end, right? This is a fact table which might just have no actual things to summarize. And it could just be when, for example, tracking people who walked past you on the street, right? You might track what they looked like, the time it happened, but there's nothing to sum and there was no values to sum. All right, so that's the recap. Please do go and watch that other video. If you want to do that, it's a good primer for what we're going in today. Now, the main topic of today is going to be optimizing our models. And when we say models, right, that's the data combined in import mode. And in order to do that, we'll just go through again, just recap on direct query, import mode, what those differences are. And then when we say optimize them, we're talking really here on ways on we're going to reduce the data. Now, we're not going to look necessarily on exactly how we do that today. That's going to be covered in detail in tomorrow's session on architecting models. Or if you're watching this on repeat, a session's probably already happened. So it'll be session number 3, episode number 3 in this series. Today, though, in order to really understand how we improve and how we can optimize, obviously we have to understand how to measure and what we want to optimize, how to identify problems. So that's what we're going to be doing today. Before we get too detailed though, we're just going to have a little review of connection types. So there's two, when I say connection types, we're two of the typical ones. You could argue there's other things like live connections, but we're not going to talk about that today. Really, we want to say there's the import or the direct query mode when you get data. The import mode does what it says on the tin, right? It imports data into Power BI Desktop and then into the service. And as you interact with it, Power BI has this data really close to your report. Your data is right there. It's already loaded. And again, this is where you do your data refreshes. Direct query, we don't actually import that data. So when we say import, right, we're copying data from the source systems, from our databases, our Excel tables, wherever it is, We're copying it into Power BI. Direct query doesn't do that. And as you interact with the report, Power BI actually sends queries back to the data source. So we'll see a little example of this now. So let's look at this import mode firstly. So one thing we do notice is that we do have here both. We have a data set, which is the imported data set, and then a report. And this report here, this is the visuals. So when you build graphs and visuals, you see the report, right? This is what we see when we go to powerbi.com and click on a report. But in import mode, when we choose import mode, it does have this data imported in the background. Even if you do this all in one file, sometimes you import in Power Query, you build your report in the same file. In the service, when you powerbi.com, when we publish it, it does actually spit this out, and you'll be able to see that, right? When you have a workspace, when you go to the workspace and you look at the artifacts in it, you'll see that there's a data set and there's a report, even if you did it together. So always good to think of these as separate elements. So what happens in import mode, right? Back. So data is copied from the source, scheduled intervals. So the databases, this is cloud, wherever, data is copied over from there, and it's copied into powerbi.com, where complex ETL can happen. So ETL transformations, right? So a user looks at the report, and our business users come and look at the report, and the report gets this data from the data set directly. So it doesn't go back to our source systems, our databases. It goes and looks at this data, which is copied into the service. Right? And it's copied over. It can be refreshed at intervals, and we can have complex transformations. Because this data is right there, the report's quite quick, assuming it's set up with correct DAX. Direct query, though. Here, you notice that there's no data set. We still have some data model metadata in terms of what relationships and measures, but the data itself is not copied over. So this really comes the other way. So a user is going to look at a report, right? So a user looks at a specific report, and they might interact with a specific visual or apply a filter. Now, the specific information is needed, and it's going to go and query this directly from our database. So as you look and as you apply filters, it's going to send specific queries just to get the information to populate what you're looking at on the report. So data is not stored on powerbi.com. Might have some cache data, but nothing's copied over in terms of like import mode. Because of this, you're sending queries back to databases, and not every data source can handle it. But typically something like a SQL database, you're sending queries every time you interact. So you can't do much transformations. If the data is not in the way you want it to be already, you can't do transformations because this is kind of on the fly. It can be a little slower, and tends to be, because as you can imagine, this data is a bit further away. It's stored in the database. Power BI has to go externally, get the data once, bring it back and display it. Of course, the big advantage is it is always up to date from within when you interact with it, because the data is being getting and retrieved almost in real time. Maybe with a delay as much as the user is looking at it. So then when we think of a data set, right, and this is that brown the brown symbol you see with the database and its model data set, there's two elements. The first is the metadata, and this takes information. We call this the TOM, the tabular object model. This stores all information about our columns and our relationships and our measures and things like that. This is where, when we do all the modeling and do the relationships, drag things together, this is the information on how Power BI is going to propagate filters and how it's going to display. So this is really true in both import and direct query, because in direct query, we still need to say, what the data sets are and how the tables relate. However, the data is stored in import mode. So this is the actual data when we say we copy it over, right? And this data is quite large in size. So what we're going to focus on today is import mode. And it's really looking at this right-hand side, this data. So we're thinking, what can we do in order to optimize this data? Because Power BI does do some optimization techniques to make sure that this data is stored in the most efficient way as possible. This is really important because as we grow and as we get more data, there's a direct cost related to this, right? We'll need to scale up our nodes. Every Power BI file has limits depending on your licenses and stuff, but for the most part, when we develop, we want to try and keep this small because there is direct costs related to it. And if it's inefficient, it could slow down our reports. So when we are looking at building good reports that we think are going to last a long time, because another reason, typically we add data to reports as time goes on. It's rare that the data in a report goes down. So knowing that, our goal should always be, let's make this data smallest size impossible. And how do we do that without actually reducing the data in the report? We take advantage of the compression mesh methods. This is of what we call the xVelocity, or is more commonly known as the VertiPaq engine. And it does all these compressions on the data to make sure it's in a nice state, and it keeps it nice and small and efficient. Now, a lot of different ways as well we can set up, our metadata. We can set up different tricks to try and do this. We'll look at that really in depth tomorrow or in session 3 if you're watching on repeat. And that's going to be architecting data models, right? Different tips and tricks for this. However, before we can do that, we've got to understand what the compression is and how the back engine actually does this compression and what it does behind the scenes. So I will say, if you want to get really deep into this, SQL BI have a really good paid course on tablet editing and modeling. Those two are great if you can you are available to watch them. They do have a cost. They are paid. They're probably the best in the world, I would say, that I've seen on this. We're going to go through though quite a bit more high level now in the next hour, but with enough information to understand the basics of how this works, what's happening in the background, so that when we come tomorrow, armed with our knowledge of databases and keys and fact tables, and armed with our knowledge of compressions and the engine, we can combine these and think of cool ways to reduce this and to make it efficient. All right, so we're going to go through 3 different aspects that make up the size of your data. And we'll go through and then we'll see an example at the end. So the first one is called column data. So looking at our model, looking at our import mode, how do we do this? What is the first thing that we need to take into account when we're thinking of ways of understanding the compression and the memory it's used in the background? So the first is just data. You can see, imagine that we have these 3 columns here. Now, Power BI does something called columnar store, right? So instead of storing like we would a CSV, which is a row store, and we store things row by row, Power BI actually, in the background, and VertiPaq, the engine. When I say VertiPaq, I mean the engine behind the import mode of Power BI. It stores things differently. It stores things in columns, and then we look at the data size of each column. Now, it's a bit of a different technique, and you'll see why it does this and what advantages this brings. But the first thing is just simply it splits columns individually and stores them that way, rather than a CSV, which splits rows individually. And what makes up a column? Well, it just has data in, and obviously, computers work on bits and bytes, right, and megabytes, this kind of stuff. As you can imagine, the more information in a column, the more data it's going to have. So you can see this middle column B, right? And these data sizes are completely made up, and purposely so, because the numbers aren't really that important. I just want to emphasize the point. Column B just has 1, 2, 3, 4, 5 in it. That data is going to be quite small because there's not as much data. Column C, has a lot bigger texts, and this data size might be a lot bigger. Now, it's not an exactly linear relationship. Computers kind of store things in how it bytes and stuff. Not really important here, and not going to go too depth into it. But essentially, with different data types, such as text, which contains more characters, right? This is going to be bigger, bigger storage and have more data in. So that columnar store, that's the first thing we've got to think about, really. And that's more a primer here, right? We've got to realize the columns are split up to be stored. So each column is stored individually. Obviously, the more data the column, the larger it is to store. However, more optimization is done on the columns. So actually what happens is these columns might have different numbers of rows, and they might have more information behind them. So this is one advantage it can do when we do columnar store. The rows of the columns might actually change, and we'll see why it does that. And that again is to optimize. So let's look at the first optimization technique. So we just looked at the data itself and how it stores. Let's think of an optimization technique. The first one we're going to talk about is called run length encoding. Maybe if you've studied computer science or databases and this kind of technology before, you may have heard of this. Otherwise, this might be a new technique. Let's just look at this number, right? And before you can count, I'm going to say that this number, right? If we say it out loud, it's 33333333333. I think I said enough there. 55555. Now, that's quite a big number, and it took me a while to say. If I was going to tell someone this number, I probably wouldn't say that, right? I would just say 10 threes, 5 fives. You can see that second way already, that's a lot easier. I had to say a lot less words to get that point across. So instead of saying each number, just repeating 3 10 times in a row, then repeating 5 times in a row, I can just say, maybe if you're a computer, it might be easier to kind of think of this as a pair, right? You've got a 10 threes, and then you've got 5 fives. And you can see that way, we only need 4 numbers here, maybe a couple of brackets and commas, but there's only 4 numbers to communicate what is 15 numbers in the first row. And this is really because there's repeating values. And that's the essence of run length encoding. Typically, in your columns, imagine you have sales or something like that, right? When we have sales, hopefully we're not just selling one product every single time. You'll probably sell the same product multiple times. You'll have sales on the same date. So there's going to be repeating values that go down in your fact table. And it's that thought that the likely and often is, right, repeating values in a table. That means that this method, thinking about an easier way to store repeating values, comes into effect. So let's look at it more from a data and a column point of view. So we can see here, if we look at original column A, we have one blue value. So the value of column A in the first row is blue. And this we can say, right, there's 1 because it repeats once. And then that's at position 1 because it's the first value. And then we can say there's 4 greens in a row. We can see green is repeated 4 times. And that starts at position 2 because the first green, if we look here, if we say this is position 1, this could be row number 2. So we say 1 blue and 1. Then there's 4 greens because it repeats 1, 2, 3, 4 at position 2. So we can just put these numbers there next to this for now. I'll just put these numbers, so 1 at position 1, and there's a run of 4, right? In run encoding, there's a run, we call it, of 4. That starts at position 2. And then let's look at banana or column B. There's one banana at row at position 1. Then we have 2 carrots at position 2. So there's 1, 2, and this starts at position 2. And if we look 1, 2, 3, 4, and there's 2 pairs. So we say there's 2 pairs and it starts at position 4. And let's do this for duck and hen, right? 3 at position 1, and then there's 2 at position 4. So once we see this, if we think about this now, all those values, all those rows that don't have one of these red numbers to them, they don't provide us any more information, because with these extra little bits of numbers we've provided, we've actually said all the information that we need, and we can infer and calculate what the whole column looks like. So we can get rid, and we can actually store the data like this, right? Let's get rid of those redundant values, because now these rows in these optimized columns have all the information to understand what the data looked like in the first place. And if we look at this, right? So, from the left, we can optimize down to the right. Now, obviously, this only had 5 rows. You can imagine that in 1,000,000 rows, this could be some substantial reductions, because, of course, if we're reducing the amount of rows, then we're going to reduce the amount of data that we have. So this is our first way of optimizing here. And this is called run length encoding, because we're looking for runs. So here, you may have heard of this word before. If you haven't, you're going to be hearing it a lot from now on. And it's cardinality. Cardinality refers to the number of unique values. We're going to introduce this now, because we're saying the lower the cardinality, the better it will compress. So the less amount of unique values. If you could imagine that if you have 1,000,000 rows, but they're all the same value, then you could just say there's a run of 1,000,000 and start at row 1, and your column is going to just be 1 row, right? It's going to be really tiny. If you have 1,000,000 and they're all unique, this technique isn't going to work at all, because it's all going to be runs of 1. So obviously, it depends on the least amount of unique values, the better it stores. And to be honest, you could probably, if you're going to take anything from this session today, it's that, the lower the cardinality, the better storage you're going to get, for a number of reasons, as we'll go into, but that is the most important. So really reducing the amount of unique values. Now, that might be difficult, because we're going to say, well, I can't just go and change my data. So we're looking at ways that we can work around this, and tips and tricks to do this. And of course, this works because of columnar store, right? Because we store columns separately, we can now decode this when it comes to calculation time. And if we store this row by row, this technique wouldn't really work. So because we have that columns, why we're able to store it like this. So let's look at the second part of the data, the second element that makes up an optimization. This is called dictionaries. So there's 2 types of encoding that we can do, and this is a dictionary encoding, and we'll go through, because one thing I'm not too happy with the analysis services, they like to use big and confusing words, right? We do hash encoding dictionaries and then cardinality, and so it's important. It might take a few times if this is new to you to get used to these terms, but really just try and understand what they all mean, and then have a little cheat sheet which you can come back and rewatch this video. So we said at the beginning, right? The longer the values, the more, if you have big text in your column, it's going to take more, because it has more data it has to store. So how can we reduce something like this, where the text is there, when we can't really say we're going to reduce the amount of characters, because that will change the data? So what we can do is create a dictionary. So we can say there's three different values here: banana, carrot, and pear. And we can say, let's give each one of those a number. Kind of, it's almost like an index, right? So we say banana, that's going to be number one. No reference to my to my fondness in foods, but banana is number one. We could say that then carrot is going to be value number two, and pear we can go with value number three. So then we can add some more information. Now that might sound counterintuitive, but obviously on large data sets, this can actually help. So what we do, instead of saying carrot, banana, carrot, carrot, pear, pear, we can just give it the number we added to it, like a 1, 2, 2, 3, 3. Then over here we have a dictionary table. So even though we've added some information, what we've done is we've really compressed the values in the optimized column, because this optimized column could be a million values. And instead of having a big text um, in a million times, now we just have these small numbers, which are quite small. If we only had three values, right, repeated a million times, we could just give these numbers, and then we only have to store the values once in the dictionary. This really reminds me of having a fact and dimension tables. It's the same concept, right? But instead of doing it for a table, we're doing it on each column. So this kind of works in the theory that the more data is in a column, the larger it is to store. And when I say the more data, it typically depends on your data types, right? So if you have a text column, it's going to give you a number of characters for each row, and that's going to be quite a lot of information if we want to repeat this a lot of times. So hashing coding, it builds this dictionary, and it kind of assigns internally. I say integers, right? Behind the scenes, it stores it this way, and this is a good way to conceptually view it, right? The value one takes less data than a long string value is kind of the idea. A bit theoretical here because this happens behind the scenes, but that's the idea. And again, high cardinality has high impact. If we had three unique values, our dictionary is going to be 3 rows long. If we have 100,000 unique values, our dictionary is going to be 100,000 rows long. Our dictionary is going to be the size of the amount of unique values we have, because it has to give each one a number. So it doesn't matter as much if they're repeated. And this can work along with run length encoding. And of course, we'll see why we need both as well. But these work together. I'm going to pause there if there's any questions come through on any of the social media.
We had one question come through, and I tried to answer it as best I can. Donald asks, "Does sorting the data improve your run length encoding?" And from my understanding, so just kind of going back to the run length encoding here briefly, run length encoding is optimized inside the VertiPaq engine. So as you bring data to it, the VertiPaq engine looks through the columns, and I don't know if it actually applies its own sorting, because it's trying to look at all columns, all information, right? So if you had like for example, if you had a single column that had a bunch of mixed data in it, right? And you just gave a single column to the VertiPaq engine, it would know, oh, I should just sort this thing, and it would sort the data and then apply its own partitioning or its own aggregations to compress that data. However, when you have like 13 columns, right, more columns now, the VertiPaq engine is actually a bit smarter than what humans would be able to do to figure out what is the right combination of sorting of columns to get the most compression out of that model. So that's kind of how I understand the the runtime encoding. Steve, is there anything else you'd add to that? Am I off base on there? Is that kind of how it
No, I
works?
think that's, yeah, exactly.
Okay.
And I really like that question. That's a
Yeah.
fantastic question, and that's exactly the thinking you should be doing.
Yep.
But exactly as Mike said, when you refresh this model and when it calculates,
Mm-hmm.
when it loads it from Power Query, for example, it's
Yes.
going to run an algorithm to do this.
Yes.
You can get technical, and you can even say, I want to change the amount of time I give you to think of all the possible combinations.
Sure.
Most of the time, it's gonna do this on on its best guess, right? And it might not get
Yep.
the best combination, but it'll get it pretty good. So it's going to, as Mike said, it's got an algorithm that's going to be a lot smarter than we can do.
Yeah,
So
and like in a couple columns, I think maybe humans could be okay, but when it starts getting into larger amounts of columns, that's when the algorithm takes over and kind of does a better job of figuring out the compression. However, I would say this, right? For example, if you can remove some precision, right? Things you potentially could do, and you might get into this in a little bit, Steve, but let's imagine I have very large numbers, right? I have a number with a decimal place on top of it, right? If I can get run length encoding, if I can somehow reduce the granularity of my numbers without losing precision on my data, for example, instead of, if we have, I'm just going to make up a number here, if we have things in tens of thousands, if we can abbreviate that and only do it reporting in thousands and put a bunch of extra zeros in there, you get more, to Steve's point, what he said earlier, you get less cardinality, and that would then allow the compression to happen more often, right? So I've seen techniques in very, very large data models where people will split out the whole number and the decimal number and make them both whole number columns and then fix it inside the math of the measures. So you actually have, instead of having like a decimal number, which would, again, if having decimals on numbers, potentially increase the precision required or increases the number of cardinality on a particular data column. By removing that and moving it into two separate columns, you give the opportunity to do some more compression and not having to store extra data as a decimal. So there's we're now like splitting hairs as far as like optimization techniques. There's a little things there you can do to kind of improve that still. But by and large, the algorithm's very sharp. There's been a lot of bright minds, way smarter than Steve and I, working on the algorithm to compress things so that it's optimized the best to make sure that file is small as you possibly can.
yeah, exactly right. And we'll go through techniques, as Mike said, but I think that example was great.
Yep, good example.
Getting in that thinking of reducing cardinality,
Yes,
it comes down to that at
yes.
the end of the day.
Hmm.
It's the biggest thing you can do, as Mike said, and most of what we're doing is how can we do that? So,
Yep. It
yep.
like for
With
one thing that a clean example I can give you too is, let's imagine you have text values, and you have some text values with capital letters and lowercase letters. So you may have the word Michael with capital M, Michael, or you might have it lowercase Michael, or you might have another version of that would be Mike, which might also be referenced as Michael, right? So what you could do potentially to again reduce cardinality would be is let's store everything in lowercase, so there's no difference in capitalization if that's possible for your data model, and if there are anything that's common terms that you would use, if you can make them all mean the same thing. So those are things you can do on the back end in the data warehouse side that will then reduce the cardinality and again allow higher levels of compression in your model. All right, I'll go back to your presentation, Steve. Sorry, I didn't mean to distract you there. That was a good.
no, it's
n-
great.
No other questions other than
And
that one, though.
yeah, I really, as I said, I'm glad we got that question, and it shows that people are thinking. And actually, example,
Yeah, totally.
this is what optimization is, right?
Yes.
It's just thinking, understanding how the engine works,
Yep.
and using that to advantage and having these tricks.
Exactly right. All right, back to you, Steve.
Cool. So this is hash encoding. Back to this encoding now. So the hash encoding, this works when we have uh, values in columns such as text, is a good one, and we give it a dictionary, right? It's kind of like making a dimension table, and the reason we have a star schema, it's the same thinking. However, there's another way we can do this, and it's called value encoding. So instead of hash encoding, we also have value encoding. Now this works on columns such as integers. And the whole thing about encoding is let's reduce the data in the column, right? Reducing the bytes, reducing the number of characters, really. So we saw that the best way we could do that on text is really give it a dictionary, so we only repeat the text once and therefore have less instances. However, in this example, it's pretty smart in the engine, and it says these are all numbers. They're quite long. They're not that long, but for this example, we're gonna say we want them to be smaller. So how do I make all these numbers smaller without changing the data? What it does is it looks through and it says, I can see in my column the minimum's 1,000. So that's the minimum value I have. Now, with my my goal to make the amount of characters here less, make this column smaller, I can say, what if I can take 1,000 away, because that's the minimum value, so that's the most I can take away without anything being negative. So what if I take that away from everything? So I say, let's remember the number 1,000. And now I can just take the number 1,000 away from everything. Now you can see I've done it my goal here. I've reduced the amount of characters. I've reduced the data in this column. Now I've remembered the number 1,000, right? I call this a value dictionary. It's my way of kind of visualizing this. This is more conceptual than an actual. It does store this data, but it says I'm going to remember the number 1,000. I haven't changed my data. I've changed the data in the column, but looking at my value, I know just to add 1,000 back when I want to decompress it and get the actual number. So I still have saved the values I had before. However, I've just done this in a way that's really reduced the number of data in each row. So obviously it works on single value on every row, and it works on numeric columns only, right? So you can't take 1,000 away from the word banana, right? You can't do it from a text value. So it works on numeric columns. It won't work on all numeric columns. Doesn't normally work very well on decimals because there's the range isn't there and it's not efficient. It won't work on keys as well, just an internal way for relationships when you have a table column in a relationship. But if you have nice integer values, this will work and this will be the best way. Now you can see this value dictionary is only ever going to be one row. That's a very small dictionary. So this is the best way of storing data. The most efficient is using this value encoding because it's very small dictionary and the values are typically quite small in the optimized column. If you have, as Mike was saying, if you have a way to make these repeatable and have lower cardinality, this is going to be a very small column, and this is what we love to see, some value encoding. Right? So here we have the two. The value encoding, it works by subtracting that value from every row. And then the hash encoding, which is on the right here. And that just gives it a dictionary and it removes the text to only have the text once. And it replaces these with numbers, essentially integers, to make it more efficient. So comparison, we'll dive into these what this means. If you've not seen this before, we're going to have a little example after the next few slides. But I want to just say this bottom bit here, this comes from DAX Studio. We'll go through DAX Studio quickly at the end, and we'll talk about it much more tomorrow. But what I've got here is I just did this experiment, and I made two columns in Power Query. One is this left one, and one is this right one. This column, it starts at 10,000, and there's a million values, and it just increments by one. These two columns are exactly the same. As you can see here, I've only got the first 4 rows here, but there's a million of this just going up by one. The only difference is that the one helpfully named num, this is stored as an integer. The one named text, surprisingly, is stored as a text. So what does this mean at the bottom here? I won't worry about the numbers too much because we will go into this in a second, but I really want to pay focus to this column called column size. So we can just see this top row's text, this bottom row's num. So this column size, this shows the total size of the columns, how they're stored internally. It uses DAX Studio and a really cool thing. We'll see how to do this. I won't worry too much about the numbers, but you can just see, if we just pay attention, 487 million compared to 66. Numbers don't really worry about what they mean, but this is just the total size of the column. It doesn't matter what we're measuring, but pay attention to the ratio, really. By simply storing this column as a text, the column size has gone up 8 times. My math is not that quick, but it's about 8 times as big, maybe. I'm sure someone can calculate that better than I can. The values in the columns are the same. They have identical data. And the reason is that this top one, the text is done uh, with hash encoding. Because it's a text value, even though it has numbers in, we've said this is text. So Power BI stores it as text. Therefore, it can't do value encoding. It has to use that dictionary. And we can see here it's made this huge dictionary which takes up a lot of space. The bottom one does value encoding because this is the number column, num, and it uses that value encoding, which is going to subtract, 10,000, 100,000, 10,000, 100,000 away from every number. And then you can see the dictionary is really small because it just has to remember that first number. So we can see we had 8 times compression just by changing the data type. And that's an example of how we take advantage of these compressions. So let's look at the final element that makes up a column and the final element we can take advantage of to help compression. Now, when we have Power BI and when we use VertiPaq and the xVelocity engine, we have something called an attribute hierarchy. This is an additional bit of information, an additional data that is stored about each column. So what is an attribute hierarchy? Now, to think of this, we kind of have to think of a multi-dimensional model compared to a tabular model. So we use tabular now, which is our facts and our dimensions, and they're related by relationships in Power BI. So assuming you're using a somewhat new version of Power BI that isn't many years old, and well, I think all of Power BI is, it uses tabular technology. And this is what what we used to when we talk about import and direct query. It uses tables and relationships, like we have a star schema. It's in memory. Prior to that, though, we were using multi-dimensional. So the old versions of SQL Server analysis services. This was the older technology. And this is typically where cubes come from. You can see this if you hear cube. And it has what we call attributes hierarchies, and MOLAP and ROLAP were the technologies there. This is not too important, really, on understanding all these words. If you've not seen these older models, don't really worry. It's not important. Just think of this as we now use tabular, the most up-to-date technology, before we were using something else. So why does this matter? We communicate with them in different languages. So we use DAX queries on tabular models. And this is, we hopefully have seen some DAX before. This is calculate our sums and our filters, stuff like that. But this is a new language for tabular. Before this, we had MDX queries, which kind of look like this one on the right. Not as important on how to write them, but this was the querying language for the older technology, which is still in play. Maybe there's probably still a lot of companies still using this, but hasn't been around for a few years now as the default. So what is an attribute hierarchy? Well, how cubes worked and how multidimensional cubes do work is we have this thing called an attribute hierarchy, where we'll have cubes and they're made for drilling down and drilling through. So it's really all about speed and the technology before they improved it and started using DAX. So what would happen is we would have this all feature, which we could, depending on how we stored it, it could summarize the whole of our feature. So looking at this, we're talking about outdoor protective equipment, and this is going to be a column, right? Outdoor protective equipment is a column, and then it has this all, which summarizes, and then it has what we call a leaf level, and this is all the values of that column. So kind of those unique values like we had in a dictionary. So it looks very, very similar to dictionaries, how we're using talking about dictionaries. And again, I wouldn't worry too much about the terminology here. This is called the leaf. Um, what we really want to get across is this is how the MDX worked, and it has different storage. But in order for the MDX language, it had to store this thing on the right. So this is what we call the attribute hierarchy. So it had to store this as well on each column, or it still has to store this. That's because the MDX language looks like this. We have to say we want the outdoor protective equipment, for example. I think this doesn't, and we have to specify exactly what we want to see in the MDX. So another reason for an attribute hierarchy is it pre-sorts. So in DAX, how we have to kind of in Power BI, how we have to specify the sort order by maybe another column. The attribute hierarchies can kind of have these sorted values, and it stores it, or when we do specify it, it stores it as an attribute hierarchy. And this is very important for things like month, which if we try to store any other way, sort, it doesn't make sense apart from the months of the year, which we all know what order they should be, but the computer doesn't know this. So that's another reason these attribute hierarchies are for sorting. So why are we talking about this? Why do we care, right? Why am I telling you about the older MDX technology? Because it is still used. So we have our tabular models in Power BI, which is what we use now. So we have Power BI. And what do we use in Power BI? We use DAX to send queries to the model. So every time we have a DAX query, it says, here's some DAX, tabular model, come back. That's fine. We don't need an attribute hierarchy in most cases. Other tools, including Excel, use MDX. So when you connect in Excel, when you use the connect to Excel, this uses MDX. Other tools such as SQL Server Management Studio, you can use MDX in this. So even though Power BI and we don't normally write MDX, you still have to be compatible, and we still have to support that because our tools such as Excel and others connect to the tabular model in MDX. If you were listening to our last session, episode 1, we spoke a bit about explicit measures and why we should always be writing explicit measures. Go and rewatch it if you're not sure what I'm talking about. But this is where Mike correctly said, Excel, it has to have explicit measures. And this is why. It's because it uses MDX. So we can't have these auto sum features, which uses DAX. So data models build these hierarchies in Power BI to maintain, for the most part, this MDX functionality. Now there is an option, and we'll go through this tomorrow, where we can actually turn this off. We can say, we don't want you to build this hierarchy because they can be quite large. And we'll see how to do that in Tabular Editor next session. Now, note though, when you do turn them off, you're not going to be able to use these columns in a pivot table in Excel, for example. Some DAX may be also a bit slower because some of the DAX, such as top N, I believe, actually uses this attribute hierarchy because it has that built-in sort order. So it can quickly use that. Otherwise, it will have to compute on the fly. So we have to be really careful if we want to turn these columns off. But it's very important because we will look and we'll see and exactly how the columns are made. And this will be a big impact on the storage. So let's give a summarization here. I'm not sure if we have any questions as well, but we can say, we have the data. That's the physical amount of the data in the column. And this, we have this column in our store, which means that this can be different per column. Then we have the dictionaries. We can store unique values and replace with a key. So this is the hash dictionary, which works on the text. We have that value dictionary where we remove a common number, for example, 1000, to reduce all the data, and just store the number 1000. And we have attribute hierarchies, and these are given to columns by default. Kind of the main reason for this, and then the main reason we need to care about is the needed for MDX to connect to Excel. We do have a few minutes for a quick show on how we can actually see these values, but any comments or any questions before I do that?
Yeah, good question. It's a good break there. We've had some questions come up, not really related to model size optimization at this point. It's been more around looking at or thinking through how do you handle date time transition, right? So imagine with me for a minute here, you have a fact table with a column that is date time related. And so the question really was, when should we split that date time column? Do we split it earlier in the Power Query so that we have a single column for date and a single column for time, or do we do something else? And I think it really my where I'm kind of going with this is it depends on how you want to display it in your reporting, right? If you need other dimensional pieces about that date time combination, right? I'm looking for the hour in which that time fell, or if I need to know the date hour combination, or I need to aggregate, other dimensional properties. If you my gut tells me, and again, every data model is slightly different, so you might have to tweak the design slightly based on your data model. But my thought is the fact table should retain a single column that has date time as a single column. Granted, that'll be a bit more expensive to store that information inside that fact table, but then you can actually have a dimension table that links back to that main fact table on that date time combination. Because I think in Power BI, when it stores date times, it's actually storing like an e month, right? It started from like 1900, and it stores the number of days, and then the decimal portion of that becomes the number of seconds that it takes to get to that date time stamp, right? So it's basically a decimal number that date times are stored as. So again, I'd be
What a
curious your thoughts.
wonderful segue into our next
Are
session,
you
or
serious?
into our next into our
Okay.
demo, right?
Okay. So
Um,
we're curious your thoughts on those.
yep.
I hope I
Any
explained
other
it well enough.
questions before I get into it? Yes. We get to go into a quick demo.
Oh, wait, hold on. One more question came up here too. What actions are best taken if an integer column is being hash encoded?
Instead of value.
Yeah.
So typically, we'll go through this tomorrow as well. Typically, we'll try and work out the best reason why. Often, if it's a key, this will be the reason. Keys are always hash encoded. You can't change that.
Hmm.
But there is a way in Tabular Editor to give a hint, and you can say pretty much try and use value encoding.
Yes.
It might be that you have huge ranges, or you have really big negative numbers, for example. There might be some other reasons it isn't, but you can give it this hint, refresh, and then as we see, we can go and see the difference it makes.
Hmm.
Because a lot of this is going to be, it depends, and it's going to be
Yes.
it. It doesn't really matter, what the best option is. It's knowing how to look and test it, and then seeing off your data and off your models
Yeah.
what the best solution is.
Like that. Good answer. All right.
So let's look at this
Let me
model
pause.
I
Yeah.
have.
Go ahead and jump over to the date time things because I think this is going to be good.
Yeah. So I have a big table here. And we'll go into that daytime a bit more tomorrow, but we're just going to look at analyzing it today because we're not necessarily diving down to fix everything today because we have a whole hour to do that tomorrow. But to fix, we've got to analyze first. So this is my fact table. You can see here there's only 3 tables, and the others don't really matter. I've been naughty and used some calculator columns. We won't focus that too much. But you can see I've got lots of text, and I've got datetime value here. In my datetime, though, I have also put if this is an expiry date of something. I've got the datetime value, I've got the date only, and the time only. So these 2 columns are redundant, but they're for demo purposes because this value is the date of this, and this value is the time of this. And we're just going to see the implications this has. So what I can do is I am actually using DAX Studio. So hopefully, Mike, if you can quickly rustle up a DAX Studio link, you
Sure.
just need to install DAX Studio, and it will appear in this external tools. So I'm going to click DAX Studio here, right? And here's one I've done earlier. I open DAX Studio. Now, you'll notice here, and we'll talk about this tomorrow, these are my tables I have. I actually have some more. We'll talk about why these other tables aren't, and these are extra ways of reducing our data size. It's tomorrow's topic. But what I'm going to do is I'm going to click on the advanced button here at the top, and I'm going to do view metrics. Now this is Darren Goswell and SQL BI that helped a lot with this, and it's called the VertiPaq Analyzer. And this is an amazing tool, which is I absolutely love, and it's the first thing we look at. So what's that's happened is it's opened this down here. We'll go through a lot of this tomorrow on fixes, but just in the last 5-10 minutes, we're going to go through what this means, because you probably will have seen a lot of these words before now, and we can start understanding what they mean. So once I've clicked this view metrics, it has VertiPaq Analyzer metrics. We can see different aspects. We're interested in the tables. Now, original, that was my fact table. So this is the table we're just looking at. If we open up original, we actually have each column listed here in this table. This is fantastic, this tool. We can see information about this. The first one is cardinality. Now, we remember what cardinality is. It's the amount of unique values. It tells us this top row is the table. So there's 250,000 rows in this table. And each column, it says how many unique values there are. Gives us the total table size. So we have a reference. And as we see here, we see the column size. This column size here, this is how much memory this column takes. This is optimization. We want to reduce these numbers is our goal. Now this column size is broken down. So we'll look at our first column. We can say it's a little over 13. These three values here will sum up to become this value. So to my terrible drawing here, let's maybe do that in a bit way. So these three values are the breakdown of the column size. So what is the breakdown? We have the data. The data is how much data we need to store. This is that one, we're trying to reduce that. It reduces that by compression. We can't do a lot about that. We have the dictionary, hash or value. How is it storing? We can see how small the value encoding is compared to the hash encoding. We have the hierarchy size. This is the attribute hierarchy, which maintains a MDX functionality as well as some other stuff. But for the most part, we're worried about breaking MDX functionality. We'll go through kind of the hierarchy, how we can reduce that, and how we can reduce these. But let's just have a look at what is causing our biggest issues here. We can see we've arranged this by column size. So event seconds in my table was our biggest column. It had the largest column size. If I flip over to the model, and you also get a nice percentage here. This is actually, it says percent of database. This means that this one column is 31% of my entire model, which is quite a lot, right? A third of the whole size is just from this column. What is event seconds? If I flick over, it is a decimal. This is where Mike came in earlier with his point about decimals, right? This is a floating point decimal, which is horrible because it goes on forever, right? It goes really not forever, but has a lot of precise numbers. Probably not useful because I don't think we ever really need to have this precise amount of values. But you can see it's got really detailed. We can see here it's a double. What is a double? And it's going to hash encode it. So where does this come from? Well, look, 10 million of this is the dictionary because it's so precise. There is only 4 matching values. There's 249,996 unique values. There's only 250,000 in this row. So what it's done is it's because it's a hash. So this is making that dictionary for it, for that hash encoding dictionary. So the dictionary's just listed all of these and given it a number. Because they're almost unique, this dictionary is not reducing it at all, right? It's not helping. It's pretty much just taken values out of the data and made a dictionary the same size. So there's not much compression going on. So cardinality here. To Mike's point, here we have, let's look at these three. Now, expiry date time value. You'll notice that this column is 13, right? 13 million. This has the date and time in it. It's very high cardinality. As Mike said, time is stored as a decimal and dates are stored as integers. However, when you have date time, it's going to be very high cardinality because there's a lot of seconds of a lot of dates. So for example, this first one is February 18th, 2020, 11/12/26, right? That's very precise. That very second of that specific day probably isn't repeated that much. However, what does happen is the date is probably repeated. There's a lot of whatever the sales on this specific date. And there's probably some sales on a specific time. Maybe you don't need the seconds, or you could just do the hour, in which case this would be much smaller. But by splitting this up, we're going to reduce the cardinality in both columns. Even though here we've added an extra column, you can see that expiry date time value, this is the date and time together, because of its large cardinality, it's made a large dictionary and quite a large hierarchy. It's a total size of 13. The other two together are 6.5. So it's pretty much half the size by splitting this up, even though you've added an extra column. Because you look at date only, there's only 71 unique dates. There's 81,000 unique time. By using a time dimension table, you can probably split this up even more because there's going to be less unique hours, less unique minutes, less unique seconds. So each of these individual, by actually splitting this out into more columns, and maybe we'll do this tomorrow, we'll reduce this even more. As Mike said, though, you do get some limited functionality in your reporting when you use this. I love doing this, splitting date and time, and you should have your own dimensions for them in terms of modeling and optimizing, but it reduces your functionality. So this is one of those where, have a look, is a date time value, is that blowing up your model? Often it can if you have a lot of unique ones. Then think about splitting it. If it's not, you're not worried, and you want the functionality of dragging it onto an axis, which works really nice. Maybe don't. So we're not going to have any absolutes or make any absolute statements. It's always going to be
Yeah.
learn how to see what's best for the model and then go and do that.
I think this is a good example of you getting into more of the weeds on the date. So date times, I think, is very difficult to understand how it works and what you need there. But again, the limited functionality pieces that you talk about there, it's important to understand at what you need in the visuals and what data do you need to support those visuals. So, for example, if you're putting a visual down that only has a date or a time, and not both of them together, then you can kind of sneak away and get away with this, right? You don't have to worry about that. But what usually happens in date times is people typically want to do binning or bucketing or other things as well. And so you could also think about this in addition to this, right? You might have one column in the fact table, right? Again, thinking about facts and dimensions, you might have one column in the fact table that is at date time. You might even want to think about, well, do we need precision of seconds, right? Can we get down to the most recent minute, right? Is minute enough information for us to know, right? And so I very rarely find use cases of reports where we need to go down to the second. More often than not, it's around, can I get down to the minute level? And so when you get to that point, that definitely helps you remove a lot of cardinality. It drops that cardinality substantially, and you can start thinking about that. Your fact table has a date time stamp in it, and then your dimension table has also date time in it. But now you can then add the extra dimension tables that you need for hour, minute, second kind of thing, and you can then aggregate those things at a different level there. So um, again, this is
Yeah,
one of these options you need to understand how it works, because then you can make the decisions on which way is it better, right? Is it better for us to keep it in as one column or break it out into two columns or move it all the way into a dimension table too? So that, again, there's possibilities there.
Here's how I would summarize that. If you ask a data modeler, they would say split it up.
Yep.
If you ask a visual person, they'll say keep
Keep
it
it together.
together,
Yeah,
right?
that's exactly
So
right.
it depends. I've seen date times just used in tables
Yes,
and then split that up because if it's just showing the values, if it's not used on an axis, then
exactly right.
you
Yes,
don't need them. If
exactly
you
right.
have a few date times and to the minute or to the hour, maybe you don't want to.
So one
So you can see here as well,
another question,
this
Steve.
price one.
Yeah, one more
Go
question
ahead.
for you here while you're going through this one. Another question from someone off of LinkedIn is so um, is it important? So I think there's like a distinction here as to what's happening in Power Query and where is the breakpoint between when this compression takes over between Power Query and getting it into the data model. So maybe you can give us
Yeah. So
a point there because we're having some questions around like what if I remove columns earlier in Power Query as opposed to later. The I think it's important to note here the compression is not taking what Steve's talking about right now. This compression is not happening inside Power Query. Power Query is simply applying transformations inside the Power Query engine. There's a handoff, a handshake between when Power Query is complete and then the pickup of the VertiPaq engine to then do the compression of the model. So maybe you can speak to that a little bit, Steve. Like when does that happen?
yeah, exactly right. And I think that the distinction here, we're talking about size of your model, compressing the size here today. This question would have a different answer. We have to think about optimizing our Power Query.
Yeah.
I think the specific question is if you remove columns at the beginning or the end of the query. For this, we'll put an order chart through, and then we see the order of operations tomorrow. But exactly as Mike says, this may have been related to the sort order when we're talking about that. All of that happens after Power Query on that apply step when you see everything spinning on your screen. That's when all of this is happening. However, if you want to remove the columns, I would say most likely you probably do them at the beginning of your Power Query because tomorrow we'll talk about things like query folding,
100%.
and it's going to make your query a lot quicker.
Hmm.
So we'll increase the speed probably over your refresh. The size, the memory of the saved database, because this is the database size, the physical size. Um, Not so much,
Yeah,
but it is important to make it a good Power Query as well. So obviously, yes, probably do them at the beginning,
yeah.
but not because of this, other reasons.
I have a rule of thumb that I use, especially when I'm using Power Query. I try to cut as much data out of it or filter or remove as much data as you can as early in the process, right? So if you're doing things in Power Query, if you can, if there's half of the data or half of the columns that you don't need to carry through Power Query, do it right at the very beginning. Get rid of all the other columns you don't need and get that table down to the fewest amount of columns as quickly as you possibly can. And if you think about it too, right, if you're filtering out row level data, right, if you've got a table with 10 million rows and you can apply a filter early in the query that filters it down to just 1 million, do it. Figure out how what's the largest volume of data you can remove initially and start from there and then keep weeding down from there until you get your final table shaped and designed the way you want. It will make your Power Query in general perform faster. But again, that's a distinction between what Power Query is doing and what we're talking about here, which this is all on the model side. These are all the activities of you have to assume your Power Query exercise is complete and you've handed a final table over to the VertiPaq engine, say, okay, here, Mr. VertiPaq engine, compress this, put this in the data model, and that last little step of compress and load, when you watch that little screen kind of tick through and the spinny circles happen for each table, that's what's happening. That's at that point we're now getting the table loaded into the VertiPaq engine. The compression's happening and everything's getting compressed there. Um, I know we're a little bit over time, Steve, but do you have another time for another question?
Yeah, I think we're done on the demo. Tomorrow we'll go through more in detail on this, so I'm happy just to focus if we have any questions to answer that now.
Sure. So we have another question from it looks like Elijah asking about so what does it mean when you ask what is the granularity of your table? How would you describe granularity to people?
Um, so granularity, I think, is going to be looking at very highly related to cardinality in a way.
Hmm?
Depends the lowest common denominator, I'll describe it as. So
Yep.
maybe you have sales by product by date.
Yes.
That's going to be your granularity. So 1 day per one product.
Yeah.
A different granularity could be sales by product by year. That would be, we're just doing the summary of how much we sold each year by each product. Or it
Yep.
could be by customer as well. So it's that lowest common denominator of how your dimensions interact to its the lowest level. That has a big impact on cardinality though,
Yes.
because if you're doing it by second, right, then that's going to be a lot lower, lot or higher cardinality than if you did something summarized by year. So that's what we're talking about by granularity, highly related to cardinality, but it's that lowest common denominator.
Yeah, that's a good point. I like the way you put that because I mean, I think of we talk often about what is the grain of your data. The higher the grain, meaning the more pieces of little information that you have, right? Time is a great dimension for this, right? Time is a very easy way to explain the grain, right? I could have a number of records that are at the daily level. I could have hundreds or if not thousands of transactions happening, and I can aggregate all those transactions up and say, okay, we had 10,000 transactions for the single day of March 15th, right? That's one grain of data. But you can increase that grain by 12 or 24 by saying, okay, let's increase the grain up to hour. So now you have a date and an hour time bucket. So now you can do additional reporting on that, but now you've increased the number of records because you now need to have for a single day, potentially you would need to have all of the sales accounting for by every single hour of that day, up to 24 hours. So now you've doubled your, or basically taking your data and multiplied it by a potential of 24x. And then if you go down by minute, now you've taken that 24x and now added another 60 minutes to each of those. So it keeps increasing the number of detailed records that you need to increase that granularity of the data. So yes, it gives you more capability to report on more nuanced things, but going down to the second, you could get, was it 36,000, 36,000 or 360,000 seconds in a day. So now you have, a lot more records or a lot more potential for records in the context of a given day. So when I usually build the models for customers, I'm usually trying to think about what is the highest grain I can get away with that still gives you the intent of the report. So to Steve's point, what is the lowest cardinality I can get? What is the highest grain I can achieve, but still giving you the intent and value from the report without having to go down to everything by second?
Yes, you can really see that as well. I think that's a great point here. So imagine we have 10 years of data, right? If we do this by day,
Hmm.
we can say, let's do it by year first.
Yeah,
So if we
exactly
do
right.
this by year, we're going to have 10 years because we'll have one for each year.
Correct.
Let's go down to the day level. So there's about 365, ignoring leap years.
Yep.
We times that by 10. So, 1 day of the year for each year. We're going to have that many rows, but our cardinality is, going to be 365. If we go down to the hour,
We're now increasing the grain again by another a multiplier of 24.
yeah. So we're going to say, oops, the grain is going to be 24, right?
Yes.
So you can see how there's grain. And, the cardinality for hours, if you had year, day, hour in the same column, this could potentially be your cardinality as well.
Hmm.
So it
Hmm.
has because there's 87,000 different hours of different days in 10 years.
Exactly
So
right.
we can see how this really ramps up really quickly
Hmm.
the more we include.
Do
So
do
it's
one more, Steve. Do one more in there. Go down to minutes because some I often see people doing minute increments as well on reports, and usually I typically tell people, can you aggregate your minutes up to like 15-minute intervals, right? So now you're taking yeah. So now, boom. So if you talk about granularity of data at the year, the day, the month, and then down to the individual minute, you're now looking at 5 million rows of data across 10 years of information. That can be a lot of cardinality, and that can add a lot of extra weight to your modeling. So that's why you kind of think about this in the context of, okay, how can we split this stuff out? How can we aggregate things up to a higher level? Instead of doing 60 minutes for every hour, you could do every 15 minutes, and then you can change that so that then when adjust that, yeah, so right there. So now you'd have another level of granularity that's less than minute, but you get more information there. So again, it's just really going down to the level of how detailed do you need the reporting to be to meet the end objectives of the report.
and you
So
can see here how in some cases, right, this is your granularity.
Yeah.
There's 5 million, right? Because that's the total possible.
Yep.
If we had a date table, this would be the granularity, right? Because we
Yes.
could have one date table, which would have 10 years, 365 days,
Yes.
and then a timetable, which would be 60 times 24. So there's 1440.
Yep.
So this could be the granularity of a date of the cardinality of a date in a timetable.
Mhm.
If
Versus
you had a single one,
single
this
column.
could be the potential.
Yeah.
But again, this is where you've got to make those things. Maybe here we just say, you know what?
Screw it.
Let's not do it by the minute level. Let's do it by the 15-minute level. Let's do it
Yes.
by the hour.
Yes.
Normally that's enough.
Yeah.
So it's important things that just knowing the implications,
Yeah.
just simple changes which normally cover everything.
Matthew Roach has a very interesting phrase that he uses in here. You want to transform the data as far upstream as possible and far downstream as necessary, right? So this is one of these use cases of if you can provide aggregations to these datas upstream in the data warehouse before it comes to Power BI, you can save yourself a lot of headache and keep your models much more performant. And again, every model, doesn't matter what it is, right? Every model will run faster with less records of data, right? It's kind of a, yeah, you can do some very fancy things, and yes, you can handle hundreds of millions, if not, billions. And I think Microsoft even has like a 1 trillion row demo now, I think, going with records. But they're doing a lot of aggregation in that method, so they can get you down to the grain of detail that they need. But then they also aggregate things as well, so that the performance and the speed is there. So no tool, no matter what it is, whoever tells you what it is, more data will always be slower to aggregate and calculate across. What's happening now is you're just kind of adjusting the techniques and how you're able to get the same answer from both the very granular detail and then an aggregated form of that information as well. Awesome.
If you want tips and tricks on these techniques, tune in tomorrow at the same time,
Yes.
and or watch episode 3 if you're watching on record, because that is exactly the topic of our next session.
Awesome. Well, with that, I think this is a good time to wrap. So I'm going to give it the wrap here. Steve, thank you very much. This was super fun. Good information here. A lot of solid techniques here. Some people may have not gone down to the level of, they've just used Power BI and not gone into like, how does it actually work? So I think this is a good mechanical class around just understanding the details of what's going on there. So thank you very much.
Yeah, thank you for having me. It's a lot of fun.
All right. We'll see you everyone on the next session and hopefully see you there. Take care. Have a good night.